definition of curvature that we have so far. All right, you can write k of t because you can expect curvature to vary, unlike the case of a circle, right? In the case of a circle, we showed that it was 1 over the radius of the circle. And that you could sort of, it's not an unreasonable thing to expect. I mean, you would think if you're traveling around this circle here versus traveling around that circle at the same rates, okay? Or let's think about it from this point of view. If you went this distance along the circle, whatever that is, let's say that's a distance of 10 meters, it looks like our tangent vector has changed quite a bit. Our tangent vector started out like that, and now it's pointing this way. Whereas if I started over here, in a similar position on this circle, and traveled 10 meters, because this circle has a bigger circumference, and I travel 10 meters, my tangent vector doesn't change as much. Okay? So it makes sense, so to speak, that the curvature here, k, is smaller in a circle with a larger radius. So that sort of confirms that the relationship should be an inverse relationship, which it is, and we derived that already. We already showed how to get the curvature of a circle. Okay, so recalling back to how we did that, we started off with the following. We said curvature is defined to be the norm of the rate of change of the unit tangent vector with respect to the rate of change of distance along the path. Okay? So S was measuring a small change in displacement along the path, and then we displaced ourselves a little bit along the path. We said, how much did the tangent vector change by? Okay. So what did we do next? We said this is a little complicated to calculate because finding ds would require finding an arc length parameterization, which means finding the arc length function and solving backwards for t and subbing in and rewriting things. So we decided it would be more practical to calculate it like this. And we know that's true. Okay. But then we can sort of condense this notation a little bit. All right, the thing on the top, we could just say, we'll call that t prime of t, which means the derivative of the unit tangent vector and the norm of that. And that thing on the bottom, we said the other day, if we just recall the arc length function for a minute, the arc length function was the integral from some starting number, or 0 maybe, let's let it be 0, why not, to t of the norm of r prime of u du. Okay, and actually we didn't even call it L, we called it S of t. Okay, if you take the derivative of this, which would be ds dt, then fundamental theorem of calculus tells you that the derivative of the antiderivative, you just plug this t in here and you get the norm of r prime of t. So I mention this because that's exactly what's in the denominator of this expression for curvature. So we can write norm r prime of t. Okay? Now this isn't too bad. It does require a little bit of work though. You're going to have to go find the unit tangent vector first. So recall for a minute, t of t would be the derivative of your function over the norm of that. And that could end up being a pretty complicated expression. If you try some examples, you'll see that could not be nice to look at. And then you have to take the derivative of that, t prime of t. And that could be anything. Okay? Then you divide by this thing on the bottom, which isn't so bad. All right. But you'll notice that this definition of curvature requires you to go find unit tangent vector first. Here's the goal for this lesson. It would be nice if I can just start with a expression for r of t. So r of t might equal something, and then be able to directly calculate k of t without having to go through the trouble of figuring out an expression for the unit tangent vector and then taking the derivative of it and then doing all those kinds of things. So that's the goal. Okay? So maybe I'll just give you, I'll tell you what it is, and then we'll see where it comes from. So here it is. Here's the curvature is the norm of the cross product between the derivative and the second derivative of the position function over this. Okay? So that's expression for curvature. And what's nice about it, the only thing you really need to know is R of t. And then literally you just proceed, calculate, and do your thing, and you'll get an answer. All right, so maybe we'll verify the circle when we get a chance. All right, so let's prove this. Okay, so to prove this, I just got to remind you about a couple of things. First, don't forget that your tangent vector t of t, which from now on I'm just going to write that as t, is equal to the derivative of the parameterized function over the norm of that. And that's a unit tangent vector. Okay? Then you should also recall what this thing is. Okay? As we said earlier, by reminding you what the arc length function was. Okay. So what else can we say? All right, so let's take a look at this expression here. Okay, and what we can say now is that we can sort of cross multiply if you want, multiply through by the norm of r prime. We'll get r prime equals the norm of r prime t. Or we can think of that using this expression as ds dt times t. Notice that's not a dot product, it's just a scalar times t, or an expression in t times a vector t. All right, so let's keep going. What I'd like to do now is get an expression for r double prime. So we're going to look right here at this thing and take the derivative of that. Okay. So I guess we could think of it like we could do like a product rule, for example. So you can kind of see the direction I'm heading in. So far now I have an expression for r prime, r double prime, right? And what are we going to do next? Well, if we think about the definition that I'm claiming is true, it requires the cross product of those two things right there. So that's what we're going to do next. We're going to cross these things and see what happens. Okay, so here we go. So r prime cross r double prime would equal. All right. So now what I'm going to do is I'm going to write that out in pieces. So we can write it one of two ways. We can write it ds dt t cross, because we just showed that earlier, that those are equal, this expression. So I'm going to write this whole thing, but I'll put it in brackets so we don't lose track of anything. Okay. Now, it would be nice if cross products would distribute. They do. So you can distribute this. And that rules also, we've proved that before. We've looked at why that's true. And so if we write this out, here's what we end up with. We end up with this expression. ds dt t cross d squared s dt t plus this thing. Okay. ds dt both squared times t cross t prime. Space. So I could see maybe you might be a little unsure as what happened here. That expression came from ds dt t cross ds dt t prime. Okay? And you can think of like the SDT as almost like a common factor that right? But it's not really quite that. There's a rule that tells you how you multiply that. If it had been a common factor, it would have just come out as dsdt, and it didn't. Okay? This is sort of like a, think of this temporarily, just for the time being. Think of that as being like a scalar, right? And then this vector has a scalar in it. So there's a fact of the matter that if you have a scalar in one vector, scalar in another, that when you do the cross product, those scalars get multiplied and become part of the product. And that's what happened here. Okay. So what I'd like to do is simplify this a little bit. And we got to look carefully at things, and we'll have some nice realizations. If you take a look at this expression right here, what you realize is you're taking a vector and you're crossing it with some multiple of itself. Okay? Well, when you do that, you know that any vector across itself is equal to the zero vector. This is like a bold zero, meaning the zero vector. A vector with zeros all its components. But you know if you took this product then, this zero vector, and you added it to another vector over here, that you would just get the vector that's over here on the right. So this expression reduces quite a bit. So you end up with r prime cross r double prime equals ds dt squared times t cross t prime. All right, so the next thing I'm interested in is looking at this expression here. So can we say anything about it? Can we simplify it in any way? All right, so here is a little fact that you probably might not remember. If a vector, let's call it temporarily r of t, has a constant magnitude, then r of t is perpendicular to its first derivative. And that's a fun little fact. Okay? So we should just show that real quick. All right? So in order to, I need to recall something first, or I'll say this. What are we really saying? Let's just pretend the norm of r of t is some constant c. All right? So we're going to start. I'm just going to show this little fact, a mini proof within the proof. That's how you know you're in trouble. You're a proof within a proof, then you know it's going to be a hard problem. All right, so let's just for the time being say that the norm of r and t is some constant c. So this is the constant right here. And we're going to try and show that this must hold. All right, so let's pretend we squared both sides of that. Okay? So that would be true also, automatically. We know that, right? Because this is a constant, this is a constant. We square both sides, we get the same constant. Okay, however, this expression here can be written in a different way. Okay? If you think about how you get the norm of something, you square all its components, you add them together, and you take the square root. So this one here, what you've done is you've squared all the components and you've added them together, but you haven't taken the square root. So that is really the original function, dot product itself. So that is a second way to write that. Now I like the idea that dot products are involved because dot products let me check for perpendicularity. So here we go. This should equal some constant c squared. Well, what do I know I really want? Well, if I'm trying to show this fact, I know what I really want at some point is an expression that looks like this. R of t dot r prime of t should equal 0. Because if that were to happen, then I will say, oh yeah, the dot product 0, the vectors must have been perpendicular. So that's the goal. So we know we want to get this as an expression somehow. So I know I want to get the derivative involved. It would be nice if dot products obeyed the product rule, but they do. That's also something that can be proven. I'm going to skip that one. All right, so r of t dot r prime of t plus r prime of t dot r of t would equal, well, the derivative of c squared, since it's a constant, would be 0. And now you have it. Because you have 2 r of t dot r prime of t is equal to 0. That implies that r of t dot r prime of t must be 0, because 2 can't be 0. And now the dot product 0, and we have shown what we wanted to show. So that turns out to be a really important fact to help us deal with this expression. Okay, let's go back to that proof for a minute. Just look at it one more time. Again, what did we do? We started with the following, I guess we won't say an assumption. We just decided to call the length of the function c, and then we squared it, because if the two things are equal, the square of the two things are equal. And then we had this nice realization that this thing is really the dot product of the function with itself. So that was key. Right? Once you have that, you use the product rule, and you end up getting that the dot product must be 0. The dot product is 0. You know the vectors were perpendicular. Okay, great. So here we are looking at this expression, and you might say to yourself, all right, why did he go through all that? Why did we just talk about all these things? Well, you know something about the vector t. Vector t is a unit tangent vector, which means it has a constant length. So our rule applies. That implies that t must be perpendicular to t prime. Okay? And since t is perpendicular to t prime, we get a very nice way of expressing this once we take the norm. So let's just leave it like that for now. Let's keep in mind what our goal is, because it's so easy to get distracted. Let's go back and look at it. Our goal is to prove this. Okay? So far we've built an expression for this thing on the inside. We know we need the norm of it, so that's what we're going to do now. Okay? So I'm going to take the norm of r prime cross r double prime. And over here, I'm going to take the norm of this thing. So this, first off, you'll notice I could write the norm of this expression, but it's squared already, so it's positive. I don't need to do anything with that. Okay, and then I need the norm of t cross t prime. Okay, and once I see the norm of a cross product, I get a little happy because I remember some special rule, right? The norm of a cross product, this thing, is really equal to the norm of the first vector times the norm of the second vector times the sine of the angle between the vectors. But in our case, don't forget, these vectors had to be perpendicular by the rule we just proved. So that means that this theta in here is pi over 2, and this whole expression is just 1. So we actually get something that's pretty compact when everything's said and done. We get the norm of r prime cross r double prime is equal to ds dt squared times the norm of t prime of t. All right, I might have glanced over this, but this norm here is 1 because t is a unit tangent vector. Okay, so here we are. Let's keep going. You might start to see something begin to happen here. So I'm going to re-express this the other way. I'm going to write the norm of t prime of t then would be the norm of this cross product over ds dt squared. Okay. See, now this is making me feel a little bit better. It's starting to look a little bit like the definition we mentioned, right? Here's that numerator we wanted. So there it is. We just got to deal with this denominator somehow. We've got to get curvature out of this. Okay, so let's just make one more realization that this is really the following. ds dt is the derivative of the arc length function. So we can write that as the norm of r prime, and it's being squared. Okay. Okay. So now we just need to recall one more fact. Let's not lose track of our goal. Recall that one of the definitions of curvature is the norm of the unit tangent vector's derivative over the norm of the derivative of the function. And if you take this expression here and plug it into the top, and you get exactly what you want. You get the norm of r prime cross r double prime over the norm of r prime squared over the norm of r prime. But that is just this. And that's what we promised that curvature would equal. So now you have it. You have a formula for curvature as a function, or not as a function of, but you only really need to know what the original position function is, the vector valued function r of t, and you can just follow this calculation and you'll get curvature. So let's go back to the circle for a minute. We know that r of t is equal to a cosine t I plus b sine t j. And what we're going to do is find, oh, not b, sorry, that's going to be a, because we're dealing with a circle. What we're going to do is we're going to find the curvature of this, and we're going to use our new formula. So k of t equals the norm of this over that. Okay? All right, so we sort of think about it practically, what do we need? We need an expression for r prime, an expression for r double prime. We get those two things, then we're just going to have to cross them, do some lengths, and be set. So let's get these expressions for r prime and r double prime. So r prime would equal, okay, it would have to be negative a sine t I plus a cosine t j. And while we're at it, r double prime would equal negative a cosine t I plus negative a sine t j. All right, there you go. So let's get the norm of these, I guess. We need the norm of r prime. But if you look carefully at that, that shouldn't surprise you. That's just a. If you don't believe me, let's just do this out. It's going to be this component squared plus that component squared and the square root of that expression. This is equal to the square root of, when you square this, you're going to get a squared sine squared t plus a squared cosine squared t. If you factor out a squared, you get the square root of a squared times sine squared t plus cosine squared t. But sine squared t plus cosine squared t is just 1, so you have the square root of a squared, which is just a. So there you go. All right? So for the denominator, you have norm a cubed. It's just a cubed. And the last thing we need is the cross product of these two vectors. Now, if you think about how we did cross products, we wrote it as a determinant. If you think about these vectors that we have here, we really don't do anything in the k direction. So you can get away with just putting zeros here and here, and then write in what you have. Okay, so r prime is negative a sine t cos a cosine t. And then the other vector is right there. Negative a cosine t, negative a sine t. And like I said, we put zeros on the last component because these vectors only move in a plane. They don't move in the z direction at all. All right, so let's finish this off, and then we'll be set. So the norm, well, this is not the norm yet. This is just the cross product. Let's be careful. What will we get here? We would get following. I'll write it as a vector notation here. We're going to have 0 minus 0. Then we're going to have another 0 minus 0. And then lastly, here's where it gets interesting. We end up with negative a times negative a sine t. So we get a squared sine squared t. And then you're going to have minus minus, or plus, a squared cosine squared t. So that just turns out to be 0, 0, a squared. All right? And now I'm not surprised at all, because k of t then would be the norm of that cross product we just found over the norm of that thing cubed. But the norm of this is just the length of that vector. That's just a squared, because there's no component in that direction, no component in that direction, just that. That's the only way we've moved. So we have a squared on top, and then a cubed on the bottom, and we get the 1 over a, or the 1 over the radius, that we were expecting.